Hello and welcome to today's lesson on current and forces. Our learning objectives are to describe how a magnet and a current carrying conductor exert a force on each other, show how Fleming's left-hand rule represents the direction of the force, the current and the magnetic field, and apply the equation that links force on a conductor to the magnetic flux density and the current and length of the conductor. Here we have a fairly simple circuit of a power supply, a switch and a wire which is passed through a magnetic field. When the switch is open, nothing happens. But when you close the switch, you'll see the wire actually jumps out of the magnetic field. Here we have a similar setup, again with a power supply and a switch. But in this circuit, we've got a loop of tin foil. And when the switch is closed, the magnetic field generated in that loop of tinfoil will cause the two sides of the tinfoil loop to push apart. On the left hand side we have the magnetic field shown between two bar magnets, and on the right hand side we have the magnetic field around a current carrying wire. What do you think would happen if the current carrying wire was placed inside the magnetic field between the two bar magnets, and how do you think the two magnetic fields would interact? Here you can see that the field lines between the north and south pole are actually getting stretched around the wire, and as a result the wire itself would feel a force pushing it upwards out of the field. This is what's called a catapult field. You can work out which way a wire will move by drawing field lines around and combining them together. Alternatively, you can use what's called Fleming's left-hand rule. If you take your left hand and line up your first finger in the direction of the magnetic field going north to south, and then your second finger at right angles in the direction of the current going positive to negative, then your thumb will point in the direction of the force that the wire will feel. A good way of remembering this is thumb for movement, forefinger for the field, north to south, and second finger for current, positive to negative. We've now got some questions on Fleming's left-hand rule. Make sure you pause the video at each question and write your answer in your book before going forward to see if you've got it right. In Fleming's left-hand rule, what does the thumb represent? The answer is movement. In Fleming's left-hand rule, what does the first finger represent? The first finger represents the magnetic field going north to south. In Fleming's left-hand rule, what does the second finger represent? The second finger represents the current going positive to negative. If the magnetic field's going into the page and the current is going left to right, which direction will the wire move? The wire will move upwards. If the magnetic field is going into the page and the current is going downwards, which direction will the wire move? The wire will move to the right. Two parallel wires with current travelling in opposite directions will experience a force in what direction? They will try and move away from each other. If you wanted to increase the force on the wire, what factors do you think might help increase this force? Pause the video while you have a think. One option would be to increase the current flowing through the wire. You could increase the strength of the magnetic field that it's in, or you could increase the length of the wire or the object that's in the field. In order to calculate the force on the current carrying wire, we use the equation which relates force to the magnetic field strength or magnetic flux density, the current travelling through the wire, and the length of the wire that's in the field. As an example, here we have to calculate the force on 20 centimetres of wire carrying a 2 amp current in a magnetic field of 0.03 Tesla. So here we use the equation force equals magnetic flux density times current times length. The magnetic flux density is 0.03 Tesla, the current is 2 amps and the distance is 20 centimetres or 0.2 metres. Times together, this gives a force of 0.012 newtons on the wire. Now I'd like you to have a go, see if you can answer this question in your books. What would be the force on a wire that's 5 centimetres long in a magnetic field of 0.5 millitesla if the current is 2 amps? Don't worry about the mass of the wire at this point. Pause the video now and see if you can answer the question in your book. The first step is to make sure you convert everything into base units. So the wire has a length of 5 centimetres which you convert to metres by dividing by 100 and a field strength of 0.5 millitesla which is 0.5 divided by 1000. Once you've done that, times all three numbers together and you'll find the answer is 5 times 10 to the minus 5 newtons. As an extension task, if you want, you can try and work out how quickly it accelerates given a mass of 9 grams. If you want to do that, pause the video here. To work out the acceleration, we use the equation force is mass times acceleration, and we need to rearrange it so that acceleration is force divided by mass. The force is 5 times 10 to the minus 5 newtons divided by a mass of 9 times 10 to the minus 3 kilograms, and that gives us 5.5 times 10 to the minus 3 meters per second squared. And now I'd like you to read through the next question and see if you can answer it all in the book without any further help. Don't forget to pause the video while you're working it out. To solve this next problem, we need to rearrange the equation to make current the subject, so force divided by magnetic flux times length. And then we substitute in our values for force, magnetic flux density and length, and you should find that you get an answer of 80 amps. For this next question, we're going to look at something called StarTram, which hopes to use this technology in order to launch people into space. For this first question, you need to use the equation F equals ma to find the force by timesing the mass by the acceleration. Pause the video now while you do this in your book. And now you need to rearrange the previous equation to find the current using the value for force that we've just calculated. If you're not sure how to do this, then just rewind the video to the last question where we use the same equation. And you should get an answer of about 30 million amps. And for our final activity, I'd like you to copy and complete this summary into your books. Pause your video while you're working, and then we'll go through the answers. The missing words were magnetic, direction, wire, opposite, 1.2 and downwards. That brings us to the end of today's lesson. I hope you found it useful, and thank you very much.